Lab. Designing a Hand Warmer by Alex Brinley, Siena Joy, and Charis Conwell.
Introduction. Hand warmers and instant cold packs work by transferring energy in the form of heat. This transfer is measured using a process called calorimetry. The purpose of this lab is to figure out which of the listed compounds would create the most effective hand warmer.
These compounds are magnesium sulfate, MgSO4, ammonium chloride, NH4Cl, calcium chloride, CaCl2, sodium acetate, NaCH3CO2, sodium chloride, NaCl, lithium chloride, LiCl, sodium carbonate, Na2CO3.
Background. Hand warmers are used in cold weather to heat up your hands. But how do they work? Most of these hand warmers contain an inner pouch filled with water and an outer pouch containing a solid. When the film separating these two solutions breaks, the solid reacts with the water and a significant amount of energy is released. Because this reaction is releasing energy into its surroundings in the form of heat, it is called exothermic. For the reaction to be endothermic, it must absorb heat. In order to have a large temperature change, the reaction must have a large but negative heat of solution. This means that the heat of the solution will be drastically reduced and that the surroundings, in this case your hands, will absorb the heat that the reaction, the hand warmer, gives off.
Equations. Over the course of our lab, we use the following equations. The first equation is how to calculate heat transfer. The second is how to calculate the heat of the system, as some heat will be lost to the calorimeter. The third equation is how to calculate the average temperature to be used in equation number 4, which calculates the heat lost by the solution and absorbed by the calorimeter. The fifth is the specific heat of the calorimeter. The sixth equation is used to calculate energy absorbed by the calorimeter.
Objective. Our objective is to find the best solid to include in a hand warmer. This solid should be inexpensive, safe to use, non-harmful to the environment, and, most importantly, it should produce a large quantity of heat. The cost, toxicity, and environmental effect of each solid has been determined through research. To determine the heat efficiency of the solids, we conducted the following experiment.
Hypothesis. The solid that generates the largest change in temperature, or change in heat, will be the most effective hand warmer. Magnesium sulfate and calcium chloride are predicted to generate the most heat, in comparison to the other selected solids, and it is expected for them to be the best materials for our hand warmer.
Methodology for the heat capacity of the calorimeter. We will now explain our steps to finding the heat capacity of the calorimeter. It is important to note that we constructed our calorimeter by nesting two styrofoam cups together. Our calorimeter was not sealed. Step 1. Collect materials consisting of a calorimeter, distilled water, a thermometer, a stirring rod, beakers, a graduated cylinder, and a hot plate. 2. Measure 100 milliliters of distilled water into the graduated cylinder and transfer into the calorimeter. 3. Measure the initial temperature of the water. 4. Heat approximately 125 milliliters of distilled water to between 60 and 70 degrees Celsius using the hot plate. 5. Measure 100 milliliters into the graduated cylinder and record the temperature. 6. Immediately pour into the calorimeter. 7. Record the resulting temperature, Tmix, after 20 seconds. 8. Calculate Ccal using equation number 5. Methodology for examining the compound. We will now explain the process which we use to evaluate the effectivity of our various solids. Step 1. Obtain a calorimeter, a thermometer, distilled water, a graduated cylinder, a scale, a weighing dish, and magnesium sulfate. 2. Measure 100 milliliters of distilled water in a graduated cylinder and transfer to the calorimeter. 3. Record the initial temperature of the water. 4. Measure 5 grams of the magnesium sulfate into a weighing dish. 5. Quickly add the compound into the calorimeter and insert a thermometer, using it to stir. 6. Monitor the temperature and after 20 seconds record either the highest or the lowest temperature. 7. Clean up the workspace, then move to the next station. 8. Repeat with the rest of the compounds. Results: cost efficiency, environmental risk, and toxicity. After conducting our experiment, we researched factors which would contribute to the safety of whoever was using our hand warmer. These factors included cost, risk to the environment, in terms of degradation to the environment during production, or in terms of how much of the compound it would take to kill an organism, and toxicity, when the compound is orally consumed. Calcium chloride looked the most attractive, according to these factors exclusively. Results: analyzing temperature. We recorded our experimental results by considering the change in temperature before the compound was introduced into the water, the solution's temperature after 20 seconds, and the difference between the two, when the initial was subtracted from the final. We were looking for a significant positive change, and calcium chloride looked the most attractive. Since the volume of all the compounds were the same, as well as the specific heat, the actual value of the heat of solution was directly proportional to the change in temperature.
Ranking. We rated our solids on a scale of 1 to 10, 1 being excellent and 10 being poor. The categories were heat effectivity, cost efficiency, environmental safety, and toxicity. We then averaged the scores, excluding environmental safety, as limited research did not allow a full understanding of the environmental effects of each of our compounds. Magnesium sulfate, calcium chloride, and sodium bicarbonate were our lowest ranking compounds once the scores were calculated, meaning that they were our top 3 picks for effective solids.
Discussion. Our top 3 compounds were magnesium sulfate, sodium bicarbonate, and calcium chloride. While magnesium sulfate and sodium bicarbonate ranked well, they were not particularly heat efficient. Calcium chloride, on the other hand, was extremely heat efficient and pretty inexpensive. While it was toxic when ingested, we believe that heat efficiency and cost efficiency are the most important factors when choosing what compound to include in a hand warmer. A warning label on the packet could help minimize any health risks that this decision causes. Future work. Following this lab, there remain ideas that we would like to explore. We know, through life experience, that many warmers contain a gelatinous substance. Are hand warmers that are made with a gel more effective than ones that are not? If so, why? Secondly, in the name of environmental friendliness, is it possible to engineer a hand warmer that is biodegradable, and yet still effective? Lastly, we would like to explore the various ways that a person could keep a warmer close to their skin without having to hold it, possibly by lining their clothes.
Error analysis. While we noticed no glaring mistakes in regards to our lab procedure, there are many things that we could have done to come to more specific conclusions. To begin, we could have constructed a sealed calorimeter in order to increase the accuracy of our temperature readings. Conducting the experiment without a sealed calorimeter meant that our temperature readings were slightly inaccurate, as the heat could easily escape. In addition, we could have conducted multiple trials for each compound, which would have eliminated any outliers in case we made mistakes that we were unaware of and had inaccurate readings. Supplementary research may also be necessary to ensure that our ratings are completely accurate, as we could not find reliable sources on the environmental impacts of some of our compounds. Citations. On behalf of our lab group, we would like to thank these sources.
This concludes our presentation. Thank you for watching.